morning, ladies and gentlemen. Today we're going to be talking about equilibrium. This is a spring scale, and it's calibrated in newtons. And what I'm going to do is I am going to add a 1 kilogram mass to the spring scale. And, well, what's going to happen?
You're going to weigh it. What do you want to call that?
9.8. That's
Yeah.
like spot on now. It's about 10, right?
Yeah, it's a sneeze under 10.
Yeah. Okay, so what about, I've got a second one
You
here.
have 2 of them.
I've got 2 of them. What if I linked this second part right here to this?
Oh, there's 2 strings there. Okay, going
Yeah.
through a pulley.
So what happens when I put this on here?
Make a prediction.
Make a prediction. Come on, get on there. Okay, there we go. And here we go.
Bring it down low. Put them
can
in the
see
same
it.
line.
Ah.
What's happening now?
They're the same.
Why?
It's almost as if they're sharing.
They're sharing the load.
Sharing. It's
That
kinda
makes
like,
sense, yeah?
Yeah, it's kind of like if you were, trying to pick up a bucket or something. And you said, "Hey, can you help me with this?" And you guys both pick it up at the same time. It's lighter, right?
That's
Because you're
right.
sharing load. Okay. Now, what happens if I bring it
Whoa.
over here?
Whoa.
What's it at now?
Well, it's not 5 anymore.
It's not 5. So,
What the heck is going on?
what is going on with this? Why is it not adding? What's going on? Okay, so first of all, my markers. Where'd they all go?
Oh, I put them in.
I'm like, where is everything?
Markers.
Okay, so let's go ahead and draw some of these forces on here. First of all, we know the force of gravity is always down towards the center of the Earth.
I think we need to talk about some stuff before we do this.
Okay,
But
wait,
pull
bring
down
this
the
one
thing and let's do the do.
There we go. Force of tension.
I'm so tense.
Force of tension is a force transmitted by a rope, string, chain, cable, etc.
Uh-huh.
Force of tension is a fine example of Newton's third law, which is the force exerted by one end is equal to the force exerted by the other.
Yeah. You can't pull harder on one end than the other.
Yeah. Okay. When all forces acting on an object are balanced, when the net force sums to 0, forces are said to be in equilibrium.
Equal who?
Equilibrium. What's the most important part of this word?
It's got equal in it.
Yeah.
It's misspelled though.
Yeah, but equal.
Equal.
Most important. Okay. When the net force equals 0, the acceleration is 0 and the velocity is constant.
That makes sense to me.
Yeah.
We knew that already.
We knew this. So let's go ahead and take a look at our dynamic trinity.
This is very important.
Very important. When the net force equals 0, well, sorry. When we have constant velocity, the acceleration is 0, and we have a net force of 0.
Newton's second law, that's right.
Net force 0. Position 0, 0. Okay.
So if you have any one of these, you have the other 2, whether it's explicit or not.
Whether you like it or not. Yeah. That's the way it is.
By definition.
So, in analyzing equilibrium, establish a reference system. We're gonna do that in a second. We'll take a look at a reference system within our scales up on the board. All forces in each dimension sum to 0. Huh. Should we go back up with it?
Is that the last one?
Yeah.
Yep, okay.
Okay. Back over here with our
Careful.
force of gravity. So, force of gravity, do you want to call it 10 newtons?
That's 10 newtons. That's how much it weighs.
Yeah.
Yeah, 9.8, but we'll pretend it's 10.
Yeah. And then what else do we have on here? Is that right there?
I'm just equalizing everything because it wasn't quite in the middle.
Okay, let's go ahead and draw.
So those are the forces of tension transmitted by the strings.
I'm trying to make them look the same.
Yeah, well,
That's a little
it's good, close enough for government work.
close.
All right, so what should our
government work.
reference system be? What coordinate system should we use?
I say X and Y,
I like that.
like that. Should I just do like a little dotted line type thing?
Yeah,
Kind of like that.
yeah.
Okay, so, well, do we know what the forces are here?
Let's call them 7.
7? Yeah. Okay, so
There's
these are-
friction inside those scales, so
It's imperfect.
7 newtons and 7 newtons.
Okay.
So that means that all 3 of these.
There's no this is not an accelerating system, right? It's
You're
not
right.
moving.
You're right.
So, which means that our net force is 0, which means no acceleration, which means our velocity is constant. Okay.
Means that all the forces are canceling each other out. It's obvious. It's just sitting there.
Yeah, it's just chilling. So, let's go ahead and break this down to some components. So we've got this component
The horizontal components.
of this vector right here,
Yep.
and then the
Vertical components.
vertical components. Now,
Where's the cancellation happening?
so we know. So this is my force of gravity. These two, which we're gonna call force left and force right, they're gonna have to equal the force of gravity, right?
That makes sense. They got to cancel out. Everything in the up cancels out the down.
Force right equals the force of gravity. If our force of gravity is 10 newtons, and these are equal,
It's got to be what plus what equals 10. It's the same number. Sweet!
rocket
Sweet!
okay. And then these two are just gonna cancel each other out.
Yep.
Sweet, and we know this because our net forces are 0. It's not accelerating. It's just chilling there.
I have a question for you.
Go.
What's this angle right here?
Ooh. How can we figure this out?
I'm seeing triangles here.
I say triangle too. In fact, let me not do blue right there. Let me not do black right there. We could take a look at this, right? Let's move this over here. Right? You with me on this?
Yes.
Okay. Put that there if you want to. And let's just take a look at this one right here. Let's see.
The blue one is equal to how much? 5.
5 newtons.
What part of the triangle is that?
That's the adjacent side, right?
Yep.
So we know that the sine of theta equals opposite over hypotenuse, right?
Yep.
And we're trying to find this, so we have to do sine -1 of our opposite over hypotenuse. My opposite, oh, sorry. That's adjacent. Did I say that?
Hey, we never make mistakes.
Opposite over, adjacent over hypotenuse. Check your work, ladies and gentlemen.
See? She wrote it cosine.
Yeah, cosine.
That's her story and she's sticking with it.
Is 5 over 7. That's a 7. And let's go ahead and throw it in the calculator. Cosine 5 divided by 7. I get 44.4.
You could call that 45 degrees.
Yeah, it's pretty much 45 degrees. Okay. And if we grab
I think it's in that
our-
bottom drawer.
I was like, what do we do with it?
I think I put it.
Nope.
No.
Oh, right there. I'm very organized. ladies
No,
and
that
gentlemen.
was my bad.
Okay, so if I hold this here,
That's
okay,
about 45
if I hold
degrees.
this here, you can see. That's almost exactly 40. Oh, it's 44.4.
Woohoo!
All right. Okay, so that's all you get from me
For now.
for now. The homework is page 115 through 116. Numbers 46, 43, 54, and 52.
Do them in that order. I know it sounds crazy, but you'll see what we're talking about.
Not crazy.
Now, even if you can't solve all of them, give each one a shot. And then we'll find out how to do them, okay?
Hang in there.